The sample median, I think we may have already discussed this, but that's okay. The sample median is the middle outcome from a data set. And here's an example. If I were to randomly select 9 different MNU students and I ask you what's the median, it's going to be the middle number. Oh, are there extra papers? They're somewhere, right? Yeah, they're in the very far back corner. Isaac's got them. So here's what you do. You start off, make sure your data set is ordered from least to greatest or greatest to least. And then you mark off one from the bottom and one from the top. One from the bottom, one from the top. One from the bottom, one from the top. One from the bottom, one from the top. And then bam, right there, the middle is my sample median. Sound good?
Do you have these notes somewhere?
Not yet.
Okay.
Yeah, sorry. I was working on these up until 3 minutes ago. So they haven't been posted anywhere yet. Same deal. This time I've got 8 randomly selected MNU graduates. And suppose we were to ask those graduates, hey, what's your annual salary going to be at your new job in thousands of dollars? There's a problem. First of all, I need to write these in order from least to greatest. And that's kind of a pain, but it's important to go ahead and rewrite these numbers in order from least to greatest. So I'm doing my best here. Okay, cool. Now that they're in order from least to greatest, now I can find the median. So scratch off one from the bottom and one from the top. And one from the bottom and one from the top. And one from the bottom and one from the top. What do I do if I have an even number in my sample like this? Yeah, I just find the midpoint. So to find the median, when I have an even number of sample of my data set, I'm going to take the middle 2 outcomes or observations, add them together, divide by 2. And so this is going to be 127 over 2, which is going to be like 63.5. Okay, so that's my median. Okay. So if you have an odd numbered sample, you just pick the middle of one. If you've got an even numbered sample, pick the middle 2, add them together, divide by 2. That gives you the midpoint halfway between those. That's your median. All right. A new vocabulary word maybe is expected value. And the definition of expected value is this. The expected value is the mean of the possible values of a random variable weighted by the probability of those outcomes. So here's an example. You're at the gas station, you're thinking about purchasing a lottery ticket. Suppose you know this. Suppose you know the ticket costs $2, and imagine they're going to sell 10,000 tickets before they select a winner, and then the winner is going to receive a $15,000 cash prize. When I ask what's the expected value of the lottery ticket, it's going to be a weighted average. And there's 2 possible outcomes this time. The 2 possible outcomes is we either win or we lose. Now, if we win, we get $15,000. But the probability of winning is only 1 in 10,000. If we're going to lose, we get $0, and the probability of losing is 9,999 over 10,000. So whenever I say something like this, it's the mean of the possible values weighted by the probability. This is what I'm talking about. I say the expected value is $15,000. That's one possible value, weighted by its probability, 1 in 10,000, plus $0. That's another possible value, weighted by its probability. Of course, anything times 0 is 0, so that doesn't matter very much. But this time the expected value is going to be 15,000 divided by 10,000, so that's going to be $1.5. That's my expected value. So the lottery ticket costs me $2, but the expected value that I get from the lottery ticket is only $1.50. So if you get lucky, then you get lucky. But if you were to purchase 10,000 tickets, like you are the only one purchasing lottery tickets, you go up and you buy all 10,000 tickets, you're guaranteed to win, right? But then you're also out money because the expected value of the ticket was lower than the cost of the ticket. And this is the way it always is with the lottery. The people running the lottery want to make money, and so they will always make sure the expected value of the ticket is lower than the price. Let's do another one. Alice tells Bob that she is going to let him roll a 6-sided die labeled 1 through 6. And if he rolls a 1, then she's going to give him $1. If he rolls a 2, he gets $2. A 3 gets $3, a 4 gets $4, 5 and $6, and so on. So this time, the expected value of rolling the die would be this. It's going to be a weighted average of the outcomes. And there is a chance, there is a possible value that this is a $1 roll of the die. What's the probability that I get $1? 1/6. Yeah. And there's a possible outcome that I get $2. What's the probability? It's 1/6. And this example, assuming it's a fair die, all of the probabilities are just going to be 1/6. But this is what the expected value looks like for this situation. And if you punch this in your calculator, you should get, I want to say 350. So if you find yourself in this situation, the expected value of rolling the die is $3.50. Obviously, $3.50 is not even one of the possible outcomes. You can only get $1, 2, 3, 4, 5, or $6, but expected value doesn't have to be one of the possibilities. This is instead what it would look like if you roll the dice like 10,000 times and you calculate the average amount of money you earned. It would probably be close to 350. We would expect it to be close to 350.
Could you just add up like all the numbers, like $1, $2, 3, 4, 5, and 6, and then divide it by like the divided by 6?
Divided by 6, yeah. Because we're multiplying each time by 1/6. So you're right. That would work this time. So let's talk about the sample mean now. The sample mean is the average. And so if I wanted to find the sample mean of this data set, where again I'm talking about the height of students in centimeters, then I would just have to add up all of these numbers. And I ran out of room, but you get the idea. Add them all up and then divide by how many students we have. That's how we find the sample mean. And we used x with a bar on top, x bar, to represent the sample mean. And this is how you calculate it. Whenever we wrote out the formula earlier, we used a big capital Greek letter sigma and a little x with a lowercase I, and then divided by n. I'm going to write that a little bit prettier. And in that formula, this is the way you would see it written out if you look for a formula for the sample mean on the internet or in a textbook or something. It's probably going to look like this. The capital Greek letter sigma means it's a sum. You're going to add all of it up. Xi is talking about the ith measurement. And that is just saying, look, this guy that's 168 centimeters, that's x1. This girl that's 169 centimeters, that's x2. This girl that's 172 centimeters, that's x3. This guy over here that's 173 centimeters, that's x4, right? I'm just using the subscript to number my measurements. That's what the subscript means. So if I write a big capital sigma and then an x with a little subscript I, that sigma is telling me add up all of the individual measurements. And then n is saying the sample size. How many measurements did I take? Okay? Questions about this? Nothing yet? All right. So let's talk. The median is the middle. The mean is the average. Why would we ever want to use the median when we're talking about summarizing a data set, right? We might want to use the median because it automatically filters out what we call outliers. An outlier is a measurement that doesn't really fit with the other measurements, right? Like, I'm going to try to draw you a number line. And suppose these are all of my measurements on the number line. I've got like this sample and I might take in a bunch of measurements and they all end up over here. This measurement over here is what I would call an outlier. It doesn't fit in very well with the rest of my data. Now, if I were to take the average, then that outlier is going to have kind of a big pull on the average or the sample mean. It's going to make it skewed right. But if I use the median, my process of like eliminating the lowest and then eliminating the highest and scratching out the lowest, scratching out the highest, scratching out the lowest, scratching out the highest, that's immediately going to take out the outlier. So it kind of filters it out. It's more resilient against outliers. Why would I want to use the average? If the median is better because it filters out outliers, one reason you might still want to calculate a sample mean is because mathematically, the sample mean is the closest approximation of the expected value. This is an easy thing to say, but it's actually really difficult to prove, right? If you really love statistics and you want to take more statistics classes, then you can come back and take your calculus sequence and then come back and take mathematical statistics, and we can talk about exactly why this is the case. But other people long ago figured out that taking the average is actually the closest possible approximation we can get for trying to figure out the expected value of a random process after it's happened, after we have a sample. And so that's why we want to use the sample mean. So a median is useful for trying to gauge what the typical outcome would be. Like, one thing you might want to look up for whatever you think your career is going to be. Most people are probably going to college so that you can earn a degree, so that you can get a particular career that you have in mind. Well, look up, what's the median starting salary for a nurse, right? If you want to go into nursing. Google search median starting salary for nurses, and that way when you start applying for jobs and someone offers you a job and they tell you what the salary is, or what the hourly rate is or whatever, you know, is this above the median? Is this below the median? Am I getting a good deal or a bad deal? Likewise, if I want to know how nice a neighborhood is, I might look up what the median household income is for that neighborhood. If I want to know, who's bougier, Overland Park or Olathe? right? You might look up the median household income of both suburbs to figure out what the nicer suburb is. Well, the median is useful in this case because it kind of tells me about the typical household. It's eliminating all of the people who might really skew that average. I don't care about how many billionaires live in Overland Park because I really care about the typical household. So we don't want to use the mean, we want to use the median. When would I want to use the sample mean? Well, what if I am an engineer and part of my oil refinery uses a compressor, and the compressor has replaceable parts? Let's say I care about the impeller or the drive shaft or something and my compressor. If I'm going to run this compressor for the next 100 years, but I have to continually replace this part, I have to continually replace this impeller or replace this seal or something, I want to know what is the average or the sample mean lifespan of this part. I don't care what the median lifespan is, I care what the average is, because I'm going to replace this so many times that what I really care about is the expected value I'm going to get. Likewise, if you are a manager of a baseball team, you care about a player's batting average, not their batting median, because you are going to put that player up to bat over and over and over and over and over again, and you care about the expected value when you're going to repeat a process many, many times. So, we already said this, but an outlier is a measurement or an outcome that has an excessively large deviation from your other measurements. It doesn't fit in with the other measurements. It looks strange. If there was a student in class that was 7 foot tall, he would probably be considered an outlier because I don't see any other students that are quite that tall. There's a few tall students, but there's no like NBA players in here, as far as I can tell. The descriptive statistics, that's our next word. If you see the word descriptive statistics, those are numbers that summarize data or describe a sample. So we've already talked about some descriptive statistics. The sample mean is considered a descriptive statistic because it's summarizing my data. The sample median is a descriptive statistic because it's a way to summarize the data. Also, we've talked before about the sample mode. That's a way to summarize data, so those would all be considered descriptive statistics. We'll talk about others too in this class, maybe a little later today. Inferential statistics, we are going to kind of save this topic for the end of the semester. We haven't yet talked about any inferential statistics. An inferential statistic is going to sound like this. We know with 95% certainty that the population mean is between 5 and 7.1. Okay. So descriptive statistics are a way to summarize a data set. It's a way to summarize the measurements you take on a sample. Inferential statistics, if you hear somebody say the word inference, inferential statistics are numbers that summarize what you know about a population. Populations have innate characteristics called parameters. A population mean is an example of a parameter. And while we can't tell exactly what the population mean is, we're going to be able at the end of the semester to make inferences about it, like I know with 95% certainty that the population mean is between 5 and 7.1. I don't know exactly what it is, but I've said something about it, right? I've created a little interval, a little confidence interval is what you'd call that. And that's an example of inferential statistics. Any questions yet? Okay. So I just want to show you some notation next. We talked about how the sample mean is going to be putting a bar above my random variable, so like x bar. For the sample median, we might sometimes use an x with a tilde above it. This is a new word. The sample variance. We'll introduce this in a minute, but this is a common one. We're going to use a lowercase s squared, and then the sample standard deviation is just going to be a lowercase s. These are descriptive statistics. So this is what you calculate after you have your data set, after you have your measurements. On the other side, we've got parameters. A population mean is an example of a parameter. We'll never know what it really is, but it definitely exists. And we're going to use a lowercase Greek letter mu to represent that it's a parameter, that it's the mean. The median, you would hope that it was just a mu with a tilde above it, but it's not. The convention is that you use a mu with a little apostrophe next to it. That's just how it is. The population variance is a Greek letter sigma squared. Sigma squared is the variance. And then the standard deviation is just a sigma. So if I write this, this is a lowercase Greek letter sigma. And if I write this, this is a lowercase Greek letter mu. But I'm just teaching you the convention. I didn't make these up. This is just what people typically use when you read a textbook, when you look online. It's kind of the standard. And I like putting these side by side because if you're wondering why do we calculate the mean, the sample mean that way, it's because that's the best way we can approximate the population mean. Population mean and expected value, those mean the same thing. Why do we calculate the sample median that way? Well, that's actually the best way we can possibly try to approximate the population median. We're going to show you formulas for sample variance and sample standard deviation here in a minute. If you're asking why did we come up with those formulas, it's because it's the best way to approximate the population variance and the population standard deviation. I also mentioned this before, but I'll say it again. And I should say this too. When I say measure of central tendency, there are 3 measures of central tendency. The 3 measures of central tendency are the mean, the median, and the mode, okay? If I say measures of central tendency, I'm talking about those 3 things, those 3 descriptive statistics. Now, the other new word is resilient. We say that a measure of central tendency is resilient if the outliers don't affect it. The mode is the least affected by outliers. The median is, again, very much not affected by outliers, and the mean is the most affected by outliers. We can do a little experiment to show you this too. Let's do an experiment. I'm going to start by making a little data set. There we go. If I want to know what the sample mean is, there's my sample mean. If I want to know what the sample median is, there's my sample median. And if I want to know what the sample mode is, there's my sample mode. Okay, now this is before outliers. Hold on, I'm trying to copy paste. Copy paste, okay. What's going to happen when I add one number to this data set, but it's going to be an outlier. It's not going to fit the others. I'm going to add the number 100. Okay? I'm going to hit enter. Boop. So before I added the outlier, my mean, median, mode are here. Afterwards, the mean jumps a whole lot. It jumps from 9.7 to 17.9. The median moves a little bit. It moved from 8.5 to 10. The mode doesn't move at all. So we say the mode is the most resilient whenever it comes to adding a weird outlier into your data set. The median is pretty resilient as well, but the mean is not very resilient. The mean is easily affected by outliers. Okay? Stop me, raise your hand if you have any questions at any point during this about what I'm saying. If I say the word dispersion, dispersion refers to how much your data set is spread out. There are 3 descriptive statistics that we can talk about today that are measures of dispersion. And there are others out there, but you know, this is an intro class. This is not all of statistics. This is intro to statistics. So we're going to talk about range, variance, and standard deviation. These are ways to measure how much your data set is spread out. So I've got data set A and data set B in this picture here. Which one would you say has more dispersion? Which one is more dispersed? B. B is more dispersed. A and B have exactly the same mean. So they have like kind of the same center, same sample mean of the data set. But you're right, B is more dispersed. It's more spread out. One way to measure how dispersed my data set is with the range. And like it says here, the range is going to be my maximum value that I have in my sample minus the minimum value I have in my sample. In other words, it's telling me how much space is there between the top of my data set and the bottom. This is the range. And I can tell B is going to have a larger range. And it's kind of because it's more spread out. So a bigger range means, in general, it's a more dispersed data set. Okay? Okay. Now what about this? If again I have data set A and data set B, do these have the same range? Yeah. The range is just the maximum minus the minimum. And these have exactly the same maximum and exactly the same minimum. And so yeah, these data sets have the same range. But would you say that A and B have the same degree of dispersion? No. B is more dispersed, right? We've still spread out the measurements in B more so than A. So I show you this because range isn't the perfect measurement of dispersion, right? You could have a data set that's more dispersed but even has a smaller range than a different data set. What we really, really want here is something that doesn't just look at the maximum and the minimum, but we want a measure of dispersion that looks at every single measurement and takes into account how far it is away from the other measurements. So we want to consider the deviation of each and every point. The deviation is this. Take the measurement that you're looking at and subtract the sample mean. This is the definition of deviation. So every single measurement has a deviation. Every single measurement, we can see how far it is away from the mean. We can subtract the mean. If I were to just add up all of the deviations like this, this is the same thing as what I would get if I took the sum of all of the measurements minus how many copies of the mean? Well, every single measurement is subtracting away the mean, so there would be n copies of the mean. But remember here for a minute that the mean itself is just the sum of all of these measurements divided by n. So let me substitute that right here, and we'll end up with something like this. These n's cancel because one of them's in the numerator, one's in the denominator. And then when I take the sum of all the measurements minus the sum of all the measurements, I get 0. So we might think, okay, I care about the deviation of every point, right? What if I just add them all up? Adding up the deviation of every point would give me a measure of dispersion, right? Except it doesn't matter what those values are. It's always 0 when you add them up. So that's not going to work. We can't just add them up. Now, the obvious solution is this. The obvious solution is that we could take the absolute value of the deviations. Right? That way when I add them up, I have to get a positive number. I'm adding up a bunch of positive numbers. I have to get a positive number. That's better than just adding the deviations, adding the absolute value of the deviations. And that would be a decent measure of dispersion. Another choice that we have might not seem super intuitive right now. This is, again, one of those things where we just have to wave our hands and say, well, this is an intro class. This is not upper level mathematical statistics. This is intro to statistics. So you're just going to have to take my word for it. That instead of adding up the absolute value of the deviations, we're going to do this instead. We are going to take the deviation, and you can take the absolute value of it if you want to make sure we have a positive number, and then we're going to square it. And again, not very intuitive for you guys, because I can't really show you what all the math is doing behind the scenes unless you take a calculus class, and this is not a prereq, right? Nobody has to take calculus before you take stats. So you just have to believe me that really the math works out so that this is a better measure of dispersion. And you might know this. If you take a negative number and you square it, you always get a positive number. Because if you multiply two negatives together, that gives you a positive number. And so I don't actually have to explicitly say that I'm going to take the absolute value, because I'm going to square it anyways. And if that number happens to be negative and I square it, it becomes positive. If that number is positive and I square it, then it becomes positive, and it's fine. So we're going to add up all of the deviations squared, and that's going to be the best way to get a measure of dispersion. Again, I'm a mathematician. I really like math. I wish I could show you the whole reasoning behind that. Why do we choose the squares and not just the absolute values? There's a really great reason. It's just not in this class. So when I choose to add up all of the squared deviations, I'm going to use the capital Greek letter sigma. That capital Greek letter is going to tell me to add up all of those things. And then we're going to call this the sum of squares total. And you can abbreviate that capital SST. And this is a good way to measure how dispersed your data set is. The one drawback is now every single time I take a new measurement, it's going to increase the SST. It's going to go up every time I take a new measurement. Even if that measurement is really close to the mean, even if that measurement is really close to all of the other measurements and it doesn't seem like it should be increasing the dispersion, it will still increase the SST. So we don't like that. We have to account for that. How do I make it so that adding another measurement doesn't increase the SST? Well, what I could do is I could take the SST and divide it by my sample size. That way, adding a new measurement is increasing the SST because I'm adding a new deviation squared to the sum. But I'm also counteracting that effect because I'm dividing by my sample size. When my sample size goes up, it decreases this measure of dispersion. We're almost there. If I just tweak it a little bit, boop, this is the sample variance. You might ask, why would I divide by n minus 1 and not just divide by n? And the answer is, go take your calculus sequence, come back, take my mathematical statistics class, and I will give you a really good answer for why we divide by n minus 1. Because I promise there's a good answer there. It's just, it's too much to explain in this intro class. Okay. And then the last thing is the standard deviation. I can calculate a sample standard deviation just by taking the square root of the variance. And I'll tell you why we care about the sample standard deviation here in a minute. But these are going to be formulas you need to know. I told you at the beginning of the semester, and this is still true, that for every test you take in this class, I'm going to allow you to have 1 page of notes on the test. So like when you take your first test, I don't remember if it's next week or the week after, but you can have 1 8.5 by 11 regular sized page of notes. It has to be handwritten. It can't be typed. It can't be copied. It can't be printed in any way. But you can use 1 page of notes. I would put these formulas on your page of notes, right? I'd make sure that that's there available to you on your notes so that you can use it during the test.
Just those two, like the ones above, or the ones above not useful?
Those are useful too. I don't think on a test, I don't think I'm going to ask you specifically to calculate the sum of squares total, but this will come up later in the semester. I'll remind you of this during the last few weeks of class.
The ones above that, are those, didn't you say those aren't useful besides that one you circled?
Yeah. On this page of notes, I'm just trying to talk you through how we're coming up with this measure of dispersion. Like why we care about the deviation of each measurement. And again, I wish I could tell you why we're squaring it, but that has to be a secret. Okay. I'll tell you this. Every question that I put on your homework could be a test question. So every time I pass out your page of exercises, make sure you know how to answer those. If there's a question on your page of exercises where you need to use a formula, then go ahead and put that formula on your page of notes. Okay? Like I said, I was really running late today, so I didn't have a chance to make a homework for today yet. I just barely put these notes together for my lecture. But I'll come up with a homework before next week. Okay, so one question you might have is the sample variance. It seemed like a good idea. It seemed like it had everything we needed to measure dispersion. Why would we like to use the sample standard deviation instead? And to answer this question, we're going to calculate the variance for this sample. The variance formula is the one where we add up all of the deviations squared and then divide by the sample size minus 1. So the first thing I need before I use the variance formula is I have to find the sample mean, which means I got to take 13 plus 14 plus 15 that's supposed to be a 15 plus 18. And then I've got to divide by 4, because that's my sample size. And if you do this, my sample mean is 15. And then I go back here, and the sum that happens in the numerator is going to look like 15 minus 15 squared plus 13 minus 15 squared plus 18 minus 15 squared plus 14 minus 15 squared. Okay? It's every deviation, which is the measurement minus the sample mean, squared, and then add it all together. And then I divide by 4 minus 1, because my denominator is n minus 1. So then I have 0 squared plus negative 2 squared plus 3 squared plus negative 1 squared divided by 3. And that is going to be 4 plus 9 plus 1 over 3, which is 14 thirds, which is 4.67-ish. Yep. Okay. And now we have the sample variance. What I want to point out to you is this. These are all measurements in centimeters. This is 15 centimeters, 13 centimeters, 18 centimeters, 14 centimeters. So whenever I use this formula, the deviations are in centimeters. That's like 15 minus 15 centimeters. The mean is 15 centimeters, right? And that's going to be 0 centimeters and negative 2 centimeters and 3 centimeters and negative 1 centimeters. But then what happens when I square this? When I take negative 2 centimeters squared, now I've got this weird measurement that's 4 centimeters squared, 9 centimeters squared, and 1 centimeter squared. Add them together, I get 14 centimeters squared divided by 3, and I have an answer where my sample variance is 4.67 centimeters squared. Centimeters squared is a measure of area. It's not a length. My data set is all in length, right? It's all in centimeters. So ideally, I want a measure of dispersion that is also in the same units as my data set. I don't want a measure of dispersion that tells me about an area. I don't have an intuitive way to interpret this. Like, yeah, these lizards that we're measuring are these specific lengths, and what's the measure of dispersion? It's a measure of area. Doesn't make sense. So why do we do the sample standard deviation? The answer is, I want a sample standard deviation that has the same units as my original data set. I want to have units of length, not units of area. And so I need to know what is the square root of 4.67, and it's like 2.16. And now I can tell you that the standard deviation is 2.16 centimeters, and that's a unit of length again. And we can go back and look at what my deviations were, which were like 0, -2, 3, -1, and 2.16 kind of sounds like it could be a deviation. It kind of sounds like it fits in with this group of 0, -2, 3, -1. That's why we call it the standard deviation. 4.67 did not fit in. It did not sound like a deviation. It wouldn't sound like something you would expect to be a typical deviation from the mean, but this does. So that's good. So that's it. Range, variance, and standard deviation are measures of dispersion. Mean, median, and mode are measures of central tendency. We have even more descriptive statistics coming up though. Like, this is called the 5-number summary. I'm going to ask you on your next test to give a 5-number summary, and you got to know what this is. The 5 numbers you're looking for are the minimum of your data set, the first quartile, the median, the third quartile, and the maximum. So the only new stuff here is the first and third quartiles. And like it says, the first quartile is going to be the median of your entire data set that's below the median. Below and including the median. The third quartile is going to be the median of your data set that's above the median. Above and including the median. So it's like the top half, bottom half medians. Let me write that out here. This first quartile is the bottom half median. And then the third quartile is going to be the top half median. So I know you're still writing your notes, but let's do a quick experiment here. I've got my data set. I've got 11 measurements. I'm going to order them from smallest to largest. And so this point right here, this is my median, okay? Because it's halfway through. It's the middle point. There's 5 measurements below it, 5 above it. This point right here, I would call this one my first quartile. Why am I calling it the first quartile? Because if I look at the bottom half of my measurements, it's in the middle of those. Let's look up here. This would be my third quartile because it is in the middle of the top half of my measurements. So I've got the minimum, the first quartile, the median, the third quartile, and the maximum. Now, there's actually 2 ways to do this. This would be the first quartile exclusive, because that number says I'm not going to include the median, I'm going to exclude the median when I take my median of the bottom half. I'm using the word median like 1,000 times a sentence, I'm sorry, but it means I exclude the median and I look at the bottom half only to get that first quartile. The other way of doing it is I could say 6.5 is my first quartile inclusive. Because if I ignore the top half, but I include the median when I take my first quartile, then I suddenly have 6 measurements, and I've got to take the median of those 6 measurements, which is going to be halfway between 6 and 7. So the inclusive quartile is going to be a little bit larger for the first quartile. And once again, this would be an example of third quartile exclusive, because I'm excluding the median. But if I want the third quartile inclusive, it would be 17. Do you see why? Okay. Now Microsoft Excel is a little bit nice because it can also do these things. Like if I want the first quartile exclusive, I would type in quartile dot, and I know you can't see this because it's super duper tiny, but it's giving me 2 options. I can either type in quartile.exc for exclusive, or I can type in inc for inclusive, and then I just have to tell it that my data is in column A, and that's going to give me Oh wait, sorry. I forgot to tell which quartile, right? I gotta tell it first quartile. And that's gonna give me 6, right? Cool. What if instead I want the inclusive first quartile? I type in quartile.inc, open parentheses, my data is in column A, and then I'm going to give it the first quartile, so it's going to be that. That should be 6.5, right? Cool. So it can do third quartile as well. Any questions about quartiles? Nope.
Wait, why is it 6.5 for inclusive?
So it's 6.5 for inclusive because I'm including all 6 of these, including the median. That's what the word inclusive means, is I include the median, and then I take the median of these 6 numbers, which should be halfway between 6 and 7. So it should be 6.5.
And the bottom is inclusive would be
Yep. So the third quartile inclusive would be these 6. And you take the median of these 6 numbers, and it's halfway between 16 and 18. So it would be the 17. Okay. That's the 5-number summary.
Would you tell us if you want inclusive and exclusive?
Yeah, I'll specify which one to use on a test. The percentile is another way of summarizing, so it's another descriptive statistic. Here's an example of percentile. If we've got 3 million high school students taking the PSAT, and we sort the scores from highest to lowest, 10% of 3 million is 300,000. So if I look through the scores, and I have already ranked the students, and I look at rank number 300,000, and I look at that student's score, that's what I would consider to be the 90th percentile. So bigger percentiles always means bigger measurements, bigger numbers on your measurement scale. So and since this is test scores, it would be good to be in a high percentile. You want to be in like the 90th percentile for test scores. You don't want to be in the 10th percentile. If this were a question about running track, right? If our data set is your 100-meter dash time, would you rather be in the 90th percentile or the 10th percentile? You'd rather be in the 10th because you want your times to be shorter. So whether it's good or bad depends on the situation, but the percentile always goes with the measurement. Bigger measurement, bigger percentile, smaller measurement, smaller percentile. Here's another example. Take the population of the United States, sort it from wealthiest to poorest. There are, 328 million US residents, so 1% of the US would be 3,280,000 residents. If we were able to rank everybody according to wealth, and we found and we tracked down the person who was number 3,280,000, and we asked them, how much wealth do you have? That's what we would call the 99th percentile. Okay? And I included this because I think it's interesting. Across the bottom of this graph, again, sorry it's so small, but maybe you can see it, are percentiles. So if you're curious about what the 25th percentile looks like, the 25th percentile has $10,000 in assets in the United States. And that's also the first quartile, right? 25th percentile would be the first quartile. The median is also the 50th percentile, and they have 97,000 in assets. The third quartile would be the 75th percentile, and that's not labeled, but we have the 80th percentile. It's like $500,000. And then the 99th percentile would be 10.4 million. Of course, this is old. This is 2016, so it's a lot different today than it was in 2016. But this is an example of a graph with percentiles, and how you could use this. And I said these are the same. The first quartile is the same thing as the 25th percentile. The second quartile, you almost never see anybody ever use the word second quartile because that's the median, right? Sometimes you hear people say the 50th percentile, that's also the median. And then the third quartile is the 75th percentile. If you give birth and your doctor tells you your baby's weight is the 21st percentile, does that mean your baby is heavier or lighter than the median baby? Lighter, yeah. Smaller percentile, smaller measurement. If we're talking about weight, then it's lighter. And we're getting pretty close to the end of the notes I have prepared for today, but there's still some more left. This is what we call z-score. This is our new vocab word. Every measurement from our data set has a z-score. And I've given you two formulas for a z-score. The one on the left is what the measurement's actual z-score is. But we're never, ever going to use this formula. Maybe I shouldn't have even included it. Because why? We don't know what the population mean is, and we don't know what the population standard deviation is. Those are parameters. Those are hidden away from us. We can't ever really know what those are. The formula we're going to use is we're going to take the measurement, subtract the sample mean, and divide by the sample standard deviation. And that's going to give me the z-score for that measurement. And it just tells you how many standard deviations are you away from the mean. Every measurement is going to have a z-score. And we like z-scores because we can take z-scores and we can convert them to percentiles. In order to do that, we're kind of making a kind of a hasty assumption here. We're going to assume that our data is normally distributed. That's a whole nother topic. But if we can assume that our data follows a normal distribution, then we can convert z-scores from percentile by opening up Microsoft Excel and using equals norm.dist, open parentheses. That's where you put in your z-score, and then comma 0, comma 1, comma true, times 100. That's the formula for using Microsoft Excel. So let's do it. Let's assign some z-scores to my data set. Let's get rid of my crazy outlier, get rid of all of this stuff. And this is my data set. First thing I need is I need my sample mean. And my sample mean is average, column A, boom. The next thing I need is my sample standard deviation, which I get from stdev.s, column A. There we go. Of course, on a test, you don't have Microsoft Excel, right? You've got to have those formulas written down. You've got to use your calculator, and then you get those numbers. Now we can do z-scores. I'm going to put my z-scores in column B, and every z-score is going to look like the measurement minus the mean divided by the sample standard deviation. Okay? So in Excel, that's what I want my formula to look like. It's just the measurement in column A minus the sample mean divided by the sample standard deviation. If you've never used Microsoft Excel before, you're wondering why are there dollar signs, right? The A1 might be easy to figure out. A tells you the column, 1 tells you the row in the spreadsheet. But what about these dollar signs? The dollar signs are going to lock that cell reference in place whenever I fill down the formula. I'll say that again. But I'm going to click on this cell and grab the bottom right corner and pull it down like this. And then when I let go of my mouse button, boop, it's going to fill that formula in, so I don't have to repeatedly type that formula over and over and over and over again. But now if I click on one of these guys, I did not have dollar signs around A7, So when I moved the formula down, that cell reference moved down with it. It's not still looking at the number 1. Now it's looking at the number 11, which I like. But where I put the dollar signs around D1 and D2, those dollar signs have locked this in place. If I didn't put the dollar signs, then it would have dragged down those cell references and I would be pointing at empty cells. So those dollar signs are just making it easier for me to use Excel. It saves me a little bit of time. So in column A, I have my original measurements. In column B, I have my z-scores, okay, where I subtracted the mean and I divided by the sample standard deviation. In column C, I'm going to put my percentiles. And to get my percentiles, I do norm.dist, open parentheses, then I reference my column B, where my z-scores are, comma, 0, 1, true, close parentheses, times 100. So now I have percentiles. For this data set, what am I trying to say? For this data set, if you were the 18, measurement number 18, then your z-score is 1.37-ish, and your percentile is the 91.5 percentile, the 91st percentile, 92nd percentile, if you want to round. But it should make sense, right? Low measurements get low percentiles, large measurements get high percentiles. That's how it goes. Let's do another example. What's the average person's height? What do you think? The average person's height is like 5'6". Does that sound reasonable? What's 5'6" in inches? That would be 66 inches. And standard deviation is a little bit harder, right? In fact, maybe we should just look this up on the internet. You know, that's always possible. Average height, adult. 5 feet 7 inches. Okay. Let's do this then. Standard deviation. 7 centimeters, but let's keep this in inches. We'll just call that 2 inches for the standard deviation. And now, Garrett, how tall are you? 5'11". That would be 71 inches, right? So that's Garrett's measurement. Let's find Garrett's z-score. And then we'll find your percentile. So your z-score is going to be your measurement minus the sample mean divided by the sample standard deviation. His z-score is 2. Looking good so far. And then we got norm.dist, the z-score, comma 1, no, sorry, comma 0, comma 1, comma true, times 100. So, you're very tall, actually. You are in the 98th percentile of height, I guess. And again, this would change, right? If I have the wrong mean or the wrong standard deviation, that changes the calculation a lot. If the sample standard deviation was actually 3, that lowers your percentile, because I'm saying my distribution is more spread out, so there's more likely to be extra tall people and extra short people if I make the standard deviation larger. And so that would lower your percentile, make everybody's percentile less extreme. But that's how it works. Now, what if you don't have Excel? What if you're sitting there taking a test and I'm being mean and I'm not letting you use your laptop during the test? So how do we read this table? And I'll work a problem with you and then I'll show you how to read the table. The problem says you have a 3-month-old female baby. She weighs 15 pounds. So your baby weighs 15 pounds. The average 3-month-old female is 12.9 pounds. The weight of female 3-month-olds is normally distributed with standard deviation 2.2. And the question is, what is your baby's percentile? So to answer this question, we first have to calculate the z-score of your measurement. And the z-score is your measurement minus the mean divided by the standard deviation. And since there's only one measurement, we don't have to include the little index. We can just say this. So my z-score is going to be 15 minus 12.9 divided by 2.2. So that's 2.1 divided by 2.2. It's like a little bit less than 1. Got to get out my calculator. 2.1 divided by 2.2 is 0.9545. And now that we have the z-score, we can convert this to a percentile. I just have to find a digital version of that table that you're holding. And you get this table, let me get that watermark off there. Boop. And what we're looking at is a z-score of 9545. So that would round to like 0.95. And let me show you what I'm thinking here. I guess what we really need to do is round our z-score to 2 digits after the decimal. So this is rounds to 0.95 when I round it. Okay? And 0.95 is what I get if I were to add 0.9 plus 0.05. And so along the rows, the leftmost column, you've got increments of 0.1s, and across the top, the very top row, we've got increments of 0.01. And to get the right percentile, you have to add together the 0.9 plus the 0.05 to get 0.95. And then at the intersection of that row and that column, this is our z-score. Or no, this is our percentile, right? You use the z-score to look up the percentile. So this is our percentile. And it's not given to you as a percent, it's given to you as a decimal. And so my decimal is 0.8289. So after we looked it up in the table, we found that the decimal was 0.8289. And then how do I convert this to a percent? You multiply times 100. And I get 82.89%. That is my percentile. So here, we've got a z-score that rounds to 0.95. You look up in the table and get a decimal 0.8289. Multiply that by 100, and now that's my percentile. So if I have a 15-pound, 3-month-old female baby, that's the 82.89 percentile for female babies at 3 months old. It's on the heavy end, but it's not the heaviest baby out there. There's still 18 or 17% of babies that are heavier than that one. So helps you get a feel for like what's typical What's unusual? You probably wouldn't be concerned unless your baby was like the 2nd percentile or like the 98th percentile. That might be causes for concern, you know. Have your doctor do a few more tests at that point. But if your baby's between like the 10th percentile and then the 90th percentile, then you have absolutely nothing to worry about. And that's how percentiles can be useful. Questions? Does that make sense? How to use the table and everything? Let's do another one, just to get some practice using the table. For IQ, everybody says the mean IQ is about 100 and the standard deviation is about 15. That's how the tests are designed. If you've ever taken an IQ test, they specifically try to design those tests and score them so that the mean is 100 and the standard deviation is 15. And let's say you take a test and you find out that your IQ is 120. What would your percentile be? Well, the first step is calculate the z-score. And the z-score is your measurement minus the mean divided by the standard deviation. So that would be 130 minus 100 divided by 15. So that's 30 over 15. So your z-score is 2. And after I have my z-score, I can use the table. And my z-score is 2, so it's just going to be 2.00, right? It's going to be pretty easy, I think, to look this up in the table for a z-score of 2. In this case, there's the number 2. And what column do I use? I'm going to use the column 0, because I need 2 plus 0. So I use my table to look this up. And the number is 0.9772, if you look that up right. 0.9772. That's a decimal. We multiply by 100 and we get our percentile. And so this is the percentile 97.22. If you took an IQ test and your IQ test came back as 130, that means you're smarter than 97.22% of the population, but you're dumber than 2.78% of the population, right? That's how you interpret that. And then we moved on, we talked about 5-number summary. There's actually a 4th measure of dispersion that I want you to be familiar with. And this is called the interquartile range. This is something that I forgot to mention last time. So if you see the acronym IQR, it stands for interquartile range. And you get the interquartile range by subtracting the 3rd quartile minus the 1st quartile. So that's something you need to know. On your next test, 1 week from today, I'm going to ask you, what's the interquartile range of this data set? And to find that, you'd have to first find the median, and then you'd have to find the 1st quartile, and then you'd have to find the 3rd quartile, and then you've got to subtract 3rd quartile minus 1st quartile. That's how you get the IQR. Does that make sense? So if I had this data set, it's convenient because this one's already ordered from least to greatest. And so this is going to be my median. And if I look at only the numbers or the measurements below the median, then my 1st quartile would be 9. And I'm doing this on an exclusive basis. Remember we talked about the difference between inclusive and exclusive quartiles? To get the 1st quartile, you just look at all the numbers that are less than the median. And then you take the middle of those. It's kind of like the median of the bottom half. Yeah.
Why would you do inclusive?
It depends on if I ask for inclusive or exclusive. You know, you have to kind of know how to do both so you know the difference. What would be the inclusive quartile? Do you know?
It would be an average between 9 and 10.
Exactly. If I want the inclusive first quartile, that means I'm taking the middle of these numbers, and it's called inclusive because I'm including the mean. And so then the middle of these numbers is these two numbers, 9 and 10, so I've got to average them together to get the inclusive first quartile.
So for the IQR, would you say inclusive or exclusive if you want?
Yeah, definitely. So for an IQR, if somebody tells you what the interquartile range is, they should ideally tell you whether or not this IQR was calculated inclusive to the median or exclusive to the median, because that will change what the IQR is in the end. That's a very good question.
So our exam is going to be inclusive or exclusive?
Yeah. Yeah, I'll try to remember to specify on the exam whether I want you to do inclusive or exclusive. And if for whatever reason I forget, I don't tell you which one to use, then you can use either one and I don't care. Okay? Does that make sense? Like, I'll give you full credit whether you answer with inclusive or exclusive in that situation. But I'll try to tell you which one to use. If I don't tell you which one to use, then, you know, just use whatever you want. The third quartile, inclusive, would be what?
18.5.
Yes. Oh, sorry. I should not confuse you with the colors. Let's use blue for exclusive. But you're right. The inclusive quartile would be 18.5. The exclusive quartile would be 19. And then in orange, I'll write the inclusive was, like you said, 18.5. Because inclusive means we include the median, and it's the average of these two numbers. So, for my IQR of this data set, the exclusive IQR would be 10. And the inclusive IQR would be 9. 18.5 minus 9.5 is 9. So you're right. You're absolutely right to point that out. That the IQR is going to be different depending on how you take your quartiles.